Okay, I'm going to talk about a proof method called the pigeonhole principle. And this principle was formulated by the German mathematician Dirichlet. You might wonder why it takes a famous mathematician to talk about pigeons. Well, but there you have it. All right. Here's the formulation of the pigeonhole principle. Suppose you have k pigeonholes and n pigeons. All right, so let's stop for a moment and consider this situation before we get too much into it. So you just kind of have the idea of what's going on here. So pigeonhole, and usually you put letters in pigeonholes, but that's okay. We can put, I'm just going to put, so here's a bunch of pigeonholes. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 pigeonholes. And let's suppose I have 10 pigeons. I'm just going to make my pigeons be circles, so 10 pigeons. And I need to fit the pigeons into the pigeonholes. Okay, now, can they fit? And the answer is, obviously not. How can you fit 10 pigeons into 9 pigeonholes? Now, if they do fit, then you'll have to fit more than one in a box. So we see here that if there are more pigeons than boxes, if more pigeons than holes, if there are more pigeons than holes, then one hole must have more than one pigeon. Okay, there must be at least one hole that has multiple pigeons. Now, they might all 10 be in a single hole. You don't know. But at least one hole must have more than one pigeon if you have more pigeons than holes. All right, so with this in mind, let's go back and see what Dirichlet said, this famous mathematician. Okay, you have k pigeonholes and n pigeons. So if n is bigger than k, that is, there's more pigeons than holes, then at least one pigeonhole must contain at least 2 pigeons. All right, that's exactly what I said. Okay. Now be careful here. As I said before, there might be some pigeonholes with no pigeons at all. We're not talking about the minimum number of pigeons in a hole. We're not talking about the maximum number of pigeons in a hole. We're just saying that there is at least one hole that has 2 pigeons. If I fit 9 pigeons here, if I fill them in, I've got to put the last one somewhere where there's already a pigeon. Okay? Now, how does this work to show us some things? Okay. All right, so in the movie Cheaper by the Dozen, there are 12 children in the family. I'll prove that at least 2 of the children were born on the same day of the week. All right, so here we have a similar situation. Instead of holes and pigeons, we have days of the week and children. So what do we have here? So we have 7 days of the week. I can do that 7 holes. 1, 2, 3, 4, 5, 6, 7. And I have 12 children. I have to fit these 12 children into the 7 holes. Now we have the same situation that we had up here. There are more children than holes, so at least one day has more than one child born on it. Now, you could have all 12 children born on the same day. You really don't know. But at least one hole has more than one pigeon in it. Now, you can't say 2 holes have more than one pigeon. You could have 6 pigeonholes have 1 child, and then the 7th day has 6 children. So there's a lot of things you can't say, but one thing you can say is that at least one pigeonhole has 2 children. So at least one day of the week has 2 children. Okay, so here's how the write-up goes. Solution: there are 12 children, which are placed into 7 days of the week. So by the PHP, pigeonhole principle, some day of the week has 2 children. So this is how the form of the write-up. You have to specify your pigeons, specify your pigeonholes, and then apply the pigeonhole principle. Okay. All right, now, next one. Prove that at least 2 family members, including mother and father, are born in the same month. Okay. So let's see. What are our pigeons and what are our pigeonholes? Well, we're talking about whether they're in the same month. Up here we were talking about the same day of the week. So days of the week were our pigeonholes in problem A. So in when we're talking about months, the months are going to be our pigeonholes for part B. So they're 12 months. So they're 12 pigeonholes. Now, how many pigeons are there? What are our pigeons? Well, our pigeons are the family members because we're fitting the family members into the months. Okay, so let's see how the write-up goes here. We have 14 family members, including the 2 adults. And they have only 12 months they can born in, and those are the pigeonholes. So by the pigeonhole principle, some 2 family members must be born in the same month by the pigeonhole principle. All right, so this minor grammatical difference here, he said, by the pigeonhole principle, some day of the week has 2 children. Here he says, some family members must be born in the same month by the pigeonhole principle. But you do need to invoke the pigeonhole principle to get this result. Set up your pigeons, set up your pigeonholes, and invoke the pigeonhole principle. Okay. All right, now, part C. Assuming there are 4 children's bedrooms in the house, so that there are at least 3 children sleeping in at least one of them. All right, now we've got something a little bit different here. It's related but similar. All right, so let's see what we have here. 4 bedrooms, we have 12 children. Let's draw the picture. I ran out of room here, so I'm going to make a new one. Okay, and so here we have 4 bedrooms. They don't all have to be in a row, but it's easier for me to draw it that way. 4 bedrooms. And we have 12 children. All right. Now, how can I fit these children into these pigeonholes? Is it possible to fit these 12 children into these 4 bedrooms in such a way that you have less than or equal to 2 children in each bedroom? Okay, let's see if that's possible. Okay, 12 children, 4 bedrooms. Suppose I have less than or equal to 2 children here, less than or equal to 2 children here, less than or equal to 2 children here, and less than or equal to 2 children here. Okay? So what is the total number of children? So if we fit less than or equal to 2 children in each bedroom, then how many total children are there? The total number of children are, well, less than or equal to 2 plus less than or equal to 2 plus less than or equal to 2 plus less than or equal to 2. Okay, so this is kind of shorthand to indicate this less than or equal to 2 is going to be, let's just say this is, to be a little bit more formal, I'll call that x1, x2, x3, and x4. Okay, let me move this down. Whoops, I may have to do it in 2 stages. Move that down there, move that down here, move this down here. Okay, so I have x1, x2, x3, x4. x1 is less than or equal to 2. x2 is less than or equal to 2. x3 is less than or equal to 2. And x4 is less than or equal to 2. Okay, so what does that mean? I have some 4 numbers, they're all less than or equal to 2, so the total is less than or equal to 8. Okay, so it's impossible to fill the 12 children because I can't fit more than 8 children without putting more than 2 children in one bedroom. So it's impossible to fit more than 8 children in such a way that there's less than or equal to 2 children in each bedroom. Okay. All right, now let's think about this. Let's generalize this a little bit. Whoops, sorry. Okay. Generalize. Suppose we have K pigeonholes. I'm going to draw the very same picture, but just use some arbitrary ... And see, we'll have K pigeonholes altogether. Okay, and suppose I have n pigeons. Okay, and suppose I want to limit the number of pigeons in each hole. Okay, so the question is, what can I limit the number of pigeons to be? All right, so let's say this is, I want less than or equal to A here, less than or equal to A here, and less than or equal to A here. Less than or equal to A in each hole here. Okay, well, no, so I'll call the number in this hole x1, x2, all the way up to xk. All right, now, what do I know about x1, x2 up to xk? That has to be equal to the number of pigeons. So I have x1 plus x2 plus ... plus xk is equal to n. Okay, what do I know about how can I use this information about less than or equal to a? Well, the sum of these numbers, since each number is less than or equal to k, then the sum of these numbers is less than or equal to k times a. Okay, so what does that tell us? We have this sum is equal to n, it's less than or equal to ka, so that tells us that n is less than or equal to ka, or a is greater than or equal to n over k. So what's my conclusion here? Okay, it's not possible to fit n pigeons into k holes in such a way that the number of pigeons in each hole is less than n over k. Okay, I kind of said that backwards, but that's what this is. That is what it's showing. And there's no way to fit these n pigeons into that hole in such a way that there's less than n over k pigeons in each hole. Another way of saying that is, if I fit, so another way, if I fit n pigeons into k holes, there must be at least one hole with greater than or equal to n over k pigeons. Now, if n over k is not an integer, this still holds true. It's not possible to put a fractional pigeon into a hole, but you still will have at least one hole with bigger than or equal to this many pigeons. For instance, if n over k is 3.5, that means there must be at least one hole with 2 or more pigeons. Okay, that's what's stated down here as the generalized pigeonhole principle. Okay, this is how he writes it. If n pigeons are sitting in k pigeonholes where n is greater than k, then there's at least one pigeonhole with at least n over k pigeons. And that's what I've used here in this problem here. In this case, I had 12 children and 4 bedrooms. N over k is 3, so there must be at least one bedroom with at least 3 children. Okay? All right. Now, here's another problem. Pigeonhole Elementary School has 500 students, show that at least 2 of them were born on the same day of the year. Okay. Now, this is just a basic pigeonhole because you're only talking about at least 2 of them. So what's my n, what's my k? Well, the number of pigeonholes is the days of the year. So there are 365 or 366 because you could have leap year. So there are 366 pigeonholes and there's 500 students. So here's how you write it up. There are 500 students, only 366 days they could have been born on. So by the pigeonhole principle, some 2 students were born on the same day. Very simple write-ups. The difficulty is that you need to identify the pigeonholes and the pigeons. Okay, here we go. Number 3, there are 800,000 pine trees in the forest. Each pine tree has no more than 600,000 needles. So at least 2 trees have the same number of needles. Okay. What's the pigeonhole and what are the pigeons? Well, the pigeonholes are the possibilities. What are the possibilities? Well, each pine tree has no more than 600,000 needles. So it could have no needles, or 1 needle, or 2 needles, or 3 needles, all the way up to 600,000. So there's actually 600,000, actually there's 600,001 because you could have 0 needles on it. It could be a dead tree. So that's slightly wrong there, but that's not going to change our result. All right, and there are 800,000 pine trees. Okay, each one of these trees has 1 value of needles. There are 600,001 different possible numbers of needles.